20, okay. I'm guessing it does. All right, there I am.
Okay.
Okay. How many people have played with electricity before? Like, how many people have stuck your tongue in a light socket? No. Yeah, I mean, it's all around us, right? So you may not have played with it, but you certainly use it all the time, everything, right? And I remember when I started studying some of it, thinking, I had a hard time because it's so abstract. And when people take physics, and then they take physics with calculus, and they get to electricity and magnetism, the things they have a hard time with is kind of abstract, because you can't touch it. In fact, it wasn't until around 1900, by 1900, that we found out what atoms are made of. What are atoms made of? What are the parts of an atom? Each person give me one. Protons, okay? So they got protons, what else?
Neutrons.
Neutrons, which are hard to find because they don't have any electric charge. Protons are positive. Neutrons are neutral. And what else? Someone else? Electrons. And for some reason, we just decided to put a negative there. There's kind of a reason because there's an E plus. But so that's what atoms are made of. Cool. What moves in a wire with electric current? You don't have to memorize this so much. What moves in electric? We say there's electricity in the wire. You get a wire and there's what's moving? What moves to the lights? Anyone know? Electricity, but what's moving? Oh, good. It's a good question to ask them. Yeah, and again, what is it? Okay, the answer is electrons. Protons and neutrons make up the center of an atom. When they break apart, that's called radioactivity. So you don't really want that happening so much because some of that stuff can be high energy. And if you squeeze them together, that's usually done inside of a star, not inside of a lab. But you can do it in the lab too. And that's also a radioactive process or a nuclear reaction. So we don't want any nuclear reactions in our electric circuits just now. But the electrons go around there. And guys, check this out. Think about it. Just try to imagine, okay? When you rub stuff, one surface is getting electrons and one surface is losing electrons. In fact, people didn't know what was going on, but they rubbed stuff and they found, ooh, spark, whatever. They didn't know what's going on. In the 1800s, they kind of figured this out. So it turns out that the electrons, and it's the ones that are the farthest out from the center, that are easiest to rub off. Okay with that? Got that picture? It's the electrons. Now, with metal stuff, there tends to be, every metal atom has like 1 to 4 electrons that are really easy to move. Like they'll just go from atom to atom. You don't have to know that number, but there's a lot of atoms. And there's 1 to 4 electrons that are free. And we can make those go down the wire. So that's what's happening. As they go, everybody okay with that? Electrons are moving down the wire. What makes electricity? What makes electrons go down the wire? What can you use to make electrons move down or inside a wire? How can you make electricity? What would you use? How do you use it in your phone, or where does your phone get that electricity from?
Power.
Well, what power? What?
Battery.
Battery, right? Battery. Or power of some sort. A power supply, we say. We're going to use our lab bench. Battery, power supply, right? A solar cell. Whatever it is, something's got to make it go, right? Because these electrons, they're in here. They're in the wire, but they're just, jiggling. They're not going from one end to the other. If I go like this, do they go down? No, they're all the electrons. So my next question then is in what way do the electrons move down the wire? Is it like, I don't know which way I was going to do it. Yeah, I'll do it this way. Here's an electron. Does it move like down the wire? Kind of flow down the wire like, you guys took 101 or taking. Does it go down like that? A. You just raise your hand to vote, you'll see. Do the electrons go kind of like, and there, back, there, that, over here, that. Just kind of like that, but still making their way down there. Do the electrons go like this? Heading down the wire like that, a bunch of electrons doing that kind of thing? The wavy thing? Or do the electrons go like this? Kind of that's the word I'm looking for. That's the word I'm looking for. Where do the electrons go? Like, I don't know. Let's see. I had a fourth one that I was thinking of. Yeah, well, it's not how it works. So, okay, what do you think? A, B, or C? Just yell out a letter. Yell something. If you make a mistake, that's how you learn. The answer is B. Why? Why would the electrons move like that? What makes it go back, and what's happening as it goes down the wire? What's it bumping into? Huh? The protons in the main part of the atom. Like the main part of the atom is just sitting there. And then you got these free, crazy atoms just messing around, playing hooky or whatever. And then, but you got to make them go one way. And so this is what we're going to do. And so we're going to talk about materials a little bit. It's good news, it's a pretty simple equation. But this changed the world, right? People really fought over, should we have electric lights? Oh, we can't bring that stuff in here. Are you crazy? You're going to make a fire. Well, what are you going to do instead? We're going to have fire. We already got a fire. But, it certainly can be dangerous if you have an electric fire. So let's talk about electricity. But you've got the main atoms, and then the free atoms, the free electrons, somehow are made to go down this wire. Now let me show you a little bit, when you hook this up, how that works. So I can still imagine, and you'll see it drawn in a lot of books, you can imagine that the electrons are kind of flowing down the wire like water in a pipe. But it's really this, and it can be important to know that. Some really cool stuff, actually, that you can do. Okay, so check this out. So I'm going to imagine it kind of like this. These free electrons moving through past the atoms. And this is called an electric current, or flow. But we really know they go like this. And the way we do this is we put a battery, and you got a plus and minus side. Are electrons attracted to plus or minus? Is negative attracted to plus, or is negative attracted to minus? Plus. So this is the plus side. And does anybody know what color we use for plus in electrical stuff? Red. Get it? So positive. And we call this high volt, or V. So they would go to that side. And here we'd say this is negative or low V. But you got to create that with a battery or a power supply. Solar cells, however you want to create that. Generate with, some other way. Now the interesting thing is, just real quick, when you do the math, saying negatives are going to the right is the same as saying positives are going to the left. And so we talk about the electric current, we imagine, so I like to think of the letter I as imagine, that positives are going to the right. And sometimes you will see pictures like this, like positive like this, going this way. I hate that. Protons do not move in a wire. I hate that. And they do it in other pictures too, like you're rubbing stuff and like positives go over here. Like what, protons? You got a nuclear reaction going on? That's crazy. So just keep in mind, when you hook this up to the power supply, you're making the electrons go one way, but we talk about the current going the other way. So we're talking about electric current. This is what we calculate and talk. We know this is the other way. It's really unfortunate. I'll tell you the quick story. People didn't know what was going on, and they rub stuff, and they rub different materials, and they can make one attract to another. Rub, no, these attract, these repel, and so you got opposite. Some attract, some repel. You got two piles. You don't know what's going on. You don't know anything about electrons, and you call one plus and one minus. You go, which one? Whatever. That one's plus, that one's minus. I don't know. Whatever. And then you keep doing it, and you find out, oh, atoms are made up of these little bits. And if I stay consistent with my old experiments, though this is in the negative pile and this is in the positive. At that point, they should have just changed it. They should have called electrons positive. All that means is opposite. And then life would have been really nice. But now, whatever. Current goes in the direction opposite. If you go further, you'll need to know that. For here, you don't really. You think of electrons moving really like this. But this is the current. How much electron flow? And what happens is when they go through a light bulb or etc., they make stuff happen. They make a computer or other thing happen. Now, how fast do you think it takes electrons to get from this light switch to that? I shouldn't have messed with that one. One more month of that bank of lights. Okay, from here to there. How long does it take to get from the electrons to get from here to there? Speed of light? The electrons don't go from there to there. When I make sound, I make atoms wiggle here that make these atoms, and the atoms that are already at your ear are wiggling. This air doesn't get to your ear. The electrons are already there. And this makes it wiggle. Anyway, separate thing. Let that go. Seriously? Okay, so we're going to do a simple little math equation, but we're going to take some measurements, as you know. That's what we do. We measure all kinds of physics phenomena, and we're going to measure the simplest electric circuit. And so I made this table here, and this is worth writing down. So here's the physical thing, like a length. I give it a letter, like a capital L or lowercase l. What units would you use for length, say? Quick. Meters. Unit name is a meter. What's the unit symbol? M, right? Okay, fine. And what is it? You know what it is. Okay, now voltage. Voltage. So, this one's kind of funny, right? The length is measured in M. Voltage, the symbol for voltage is capital V, not lowercase, I'll put a little thing. The unit is volts, and the symbol for the unit is the same as the symbol for the thing. It's just the way it is. It kind of makes it easier. Like force, F is in Newton's N. Whatever, that's just the way that is. And what's up with that? Well, it makes current happen. So that's all up with that. Current, which is these negative electrons, I should have done that red, I couldn't decide, is I. I means electric current. F is force, I is current, V is voltage, L is length. And the unit of current, anybody know? Amps, or amperes if you want to call it that. What do you think the symbol for amps is? Hey. So just get used to it. And what is that? That's the, this is actually in the opposite direction of electron flow, but really, it's just how many electrons are going down the wire. That's all. So we're going to measure current. One of these meters is going to measure current. The other one's going to measure volts. And from that, we're going to calculate resistance. Now, let me tell you what resistance is. What do you think the symbol for resistance is? No, the symbol for resistance. Like force. The physical thing is force F. Resistance R. Now the unit of resistance is called, that's the letter, ohms. These are names of people. Volta, ampere, ohm. Well, the meter's not the name of person. But, and we use a Greek letter, it's a capital omega. Capital omega. Whatever. It's kind of funny looking, but there you have it. And what this does, are you with me almost? Just think about it. It limits. So if you take a car battery and you put a long screwdriver across from the plus to minus, it's going to spark. It's going to be a little scary. And if you connect a wire one end to a battery to the other, it could spark, it could be too much. It could fry your thing. So you want it to be not so much current. You don't want like maximum current, you want just the right amount. So the resistance limits or reduces current. It resists so that you don't have too much current. You want just the right amount to do whatever. You don't want to fry your phone. You need resistance. And the way you do it is you have a little piece of material. You don't use metal, but you use some of this combination of like carbon and whatever. It lets it flow, but just not too much. Is that okay? So you got two resistors you're going to play with. They're little guys. Little piece right here. The wire is all, it's got the middle. Remember, it's just the electrons in the wire, the free ones that are going to flow. But then you get to this guy, that's going to reduce your current. Just putting a little piece of carbon type stuff in there. There's different ways to do resistors, but. And then you can get just the amount of current you want. You engineer it. Are we cool with that? That's a resistor. it has a resistance measured in what units? Ohms. You're going to measure V and I and calculate R. And it should work out well, really well. Now, just so you remember this, you might get into this, but little puzzles. This is like your initiation. What is that? A puzzle. Oh, I know. Lightning. What is that?
Looks like an omega.
It's omega. What is it doing? What's the omega doing? I'll give you a hint, World Series. What's that omega doing? So this is a baseball home run. It's an home run. All right, fine. All right, what's this? It's an ohm. What kind of an ohm? Huh? So it's a, what kind of ohm might you take to the campground? Motor home. That works. Motor home. Or a mobile home. It's a mobile home. All right. Give you 2 more shots at this. Here we have a soda, a burger, maybe it's an imitation burger or Beyond Burger. Those are good, really, actually. And there's a little, what are those? What kind of fries? They're home fries. Like home fries? Home fries? All right. These are nerd jokes. Okay, so one more nerd joke. What is that? A stove. Now I had to look this up because I wasn't sure. So it's a stove. What's the inside of that is called the oven. But you got the top, so it's called. What's another word for stove? Anybody know? That is the stove top. That inside there is the oven. The whole thing is called a stove, or another word. We don't use it that much. It starts with an R. It's a range. Some stove. You don't use it that much here, but it's still going to be called a range. So then, what would this be? What is it? Keep going. You might sing it at the campground. Where's the ohm?
On the range.
Ohm on the range. Do you know that song? Do you guys know Ohm on the range? All right. Bring my harmonica. All right, anyway, so ohms. Now you know ohms. It's more ohms, more resistance. More resistance, do you think you get more or less current? Less. More volts, more or less current. Right? You just invented, what do you think this is? What's that? Hey, you got it, right? Did you get it? What is that? Little badge? Who wears a badge? Yeah, this is pretty bad. This is Ohm's Law. All right. I'll stop. I promise I'll stop with Ohm's. That's Ohm's Law. All right, that's it. There are more, I think, but Ohm's Law. And Ohm's Law says that you make a current by what? What do you use to make current? What makes current? Volts. More volts, more current. What's current resisted by or reduced by? Ohms or resistance. What's the unit of resistance?
Ohms.
Yeah, you can't forget that now. Come on now. What's the unit of volts? Or voltage? Unit of voltage is volts. That's weird. What's the unit of current? Amps. Right? That's it. That's your law. You're going to just measure those things and check out and see if this works. It doesn't always work, but it does in simple devices like this. Other type of materials, you can do some cool things, like semiconductors, and there's various things that people can do. But this is the beginning. Does everybody understand that equation? Current is created by voltage. Turn up the volts by turning up the dial on your lab table. You're going to turn it up. It'll tell you how much every like 2 volts or so. And you should get more what? If I turn up this, what do I get more of? Yeah, if I get more volts, then that'll make what? More current. It won't change the resistor. The resistor is just sitting there. You can do that too. That's another. There's all kinds of cool devices. But so if I change that, that should change. That's what you're going to do. But the R will stay the same, but you're going to do it twice. Now check this out. If I rearrange this, what's V equal to? If I just rearrange that equation, what's V equal to? Solve for that. So I solve for V, what's it equal to? I times R, right? And if I rearrange it, what's R equal to? Multiplied by R. V divided by I. That's the one you're going to use. You're going to measure V, measure I, calculate R. That's it. We're almost there. It's pretty straightforward, but it's it's like you're not even thinking about it unless you just have some sense of like, oh, making electrons go, woo. Now you have on the front page of your lab this. So what we draw is a circuit. The wires really are not all nice and neat. They're all over the place. But we make this like, it looks like friction almost, right? Like a rough surface, because that slows you down. And the resistor reduces the current. And the wire is just like that. Emitter, you've got 2 yellow boxes there. They're called DMMs. Digital multimeter, meaning you can measure all kinds of things. Current, volts, resistance. And an ammeter is drawn like that. And a voltmeter is drawn like that. This is on your front page, so you don't have to write this really. And a variable DC supply means you can adjust the voltage. That arrow means you can get more or less volts just by turning a knob. Almost there. Millimeter, milliamps is a lowercase m, but not a meter, so it's like millimeter. M means milli, and the other M means meter. But milli is 10 to the negative 3, or moving it over here, check it out. Here's where 1, 2, 3. So 1,000 milliamps, this is going to read in milliamps. Look at the screen, it'll tell you the unit. You're going to have to convert that. How many amps is that? I start the decimal place here and I move it over how many? 1, 2, 3. 1 amp. 1,000 milliamps is 1 amp. How many amps is 6 milliamps. Do it on paper. We trust our brains way too much. We think, just write it. Just go, oh, I'm going to go here. That's where my decimal place is here. It's right here. I'm going to go over 1, 2, 3. You'll need to do that. Almost done. We'll do that. Well, that's what I was going to do. Oops. No, I was going to go like this. Couldn't imagine. Okay. Now we're going to connect things up. We're going to connect this guy up with a resistor. This will make current go through the wire, but the resistor is going to reduce the current. We're going to measure how much current and how many volts. And when we do that, we got the volts divided by the current. That tells us our resistance. And it doesn't matter how much volts we put in, the current will go up, so the resistance stays the same. And so a couple of quick little circuits, and you get used to just know that initially things are always frustrating and confusing the first time through. Keep doing it and you'll surprise yourself. So series means connect one after the other. Let me show you a picture of that. So series would be, say this. Positive, this is negative. Okay, so I'm going to go like this and, yeah, do it that way. Whatever. There's a resistor, that little piece. But I want to know how much current. This is going to be hard for you, so we're going to have to help you. You have to translate this into these wires. This, guys, is your power supply. There's a plug here. There's a red little thing sticking out of it. And you're going to plug into that red end. And you gotta open your eyes. Just pause and go, oh, let me just see, what is this? Oh. And you can ask us. We'll check it. But this is plugged into the MA, or milliamp. So that's going to be my ammeter. This red one's plugged into the V, or the volts. So that's going to be my voltmeter. And you'll even see this is called a PHYS-110 on the top. Just look around. And that's a huge thing to realize. Just look around. This is a PHYS-15B+. But they're different, and it's described in the lab manual clearly. So I'm going to hook, how am I going to do this? This is my table. Power supply. And what I'm going to do is, what you're going to do. You want to know how much current's going through there? We'll stick the ammeter in series. So I'm going to just put it, doesn't matter where you put it, here or here, but let's put it here. And I'm going to put my little amp meter, you can call it, right there. And it doesn't really matter. You're actually going to use a black wire out of one side. So this is that yellow box, yellow DMM. And then you're going to use a black wire to go to one side of the resistor. And you guys, it doesn't matter where you connect here, anywhere along that metal, it's just metal. You're going to clip on there, and then you're going to clip on there, and then you're going to bring it back to the black input of the table. That's called series. So whatever goes through the table or comes out of the table goes through the ammeter, and they'll tell you how much is going through there. Pretty clever. And that's how much is going through the resistor. And if I increase this, what's going to happen here? It's going to go up, right? Current, more current. And this is variable, really. So, okay, those are what we call in series. So if things are in series, they have the same what? What's the same? This is a question at the end of the lab. What's the same here? What's flowing? Current. Which is really electrons going the other way, but we'll forget it. Whatever. Same current through, traveling through them. The same amount of electrons per second traveling through them. The same amps traveling through them. Almost there. You really do get used to this stuff. Totally doable. Anything's doable. You want to when I get good, just put it in the time. So parallel means you connect the positive sides, the high sides if you want, and the negative sides. Don't overthink this right now. You'll see. But watch what I do here. I'm going to take this circuit now, and I'm going to go like this. Again, I'll use a black. Well, I'll draw it black, even though it bothers me more than it bothers you, probably. The way I'm going to do this is I want to know how many volts. It's kind of like a ramp where you have a high end and a low end. If I put the table and I put a ramp, I got this high to that low. And if I go from that low to something higher, it's kind of more of it's a steeper, you get more velocity, if you will, in that case. High to low, we're going to measure the volts, the change from high to low. So without overthinking this too much, I'm going to connect one wire here. I'll show you what that looks like. And one wire here, and measure the voltage using the other yellow digital multimeter. And this is plenty to think about. You're really just doing this. Keep going back to volts make current, resistance reduces the current. Here's the resistor. I'm going to take this out of the table. I'm going to go into my yellow meter that's measuring amps. I'm going to go out of the yellow meter and connect it here. And then I'm going to go back from the other side, back to the table. Then I'm going to take my other yellow meter and connect on one side, high, and then the low. And so the drop across the resistor in voltage is the drop across the meter. They're equal, and so it measures. And so it has the same, and let me just say it because it's kind of hard. Same, I'll say, let me just say voltage or say it that way. Volts or voltage across. going pretty sweet, pretty quick once you get the hang of it. Hooking it up's going to be tricky, so Jonathan and I will go around. Now, you're going to take, there's going to tell you to take, this is true in this lab minute. It's a little hard to make a table and then you describe it. So it tells you what to gather, but notice that on page 55, on the next page, there's a table for you to put your measurements. So I just want to point that out. Also, it's a little bit on page, if you would turn to page 55. And at the top, that first couple of sentences is confusing. It's not really what we want to say. What it says is that in those tables, we've put the units above the columns. So you just need to put the numbers. You don't have to put the units. Just put the numbers. And when you do the Excel sheet, so when we had that issue, I didn't catch it, like, oh, you put the units in the Excel sheet, like however many meters or however many volts, you'll mess up totally. So you just put the numbers in. Because you already got the units above it. The last thing I think that I need, it should work out really nicely. Just so you, the last little thing, if you turn to page 57. Now, here's an eye test for you. Some of these are really hard. Some of these, like Jeff's done it enough with some, like, what color is that, you know? So, but you can check with each other and check with me. The rainbow goes in red, orange, yellow, green, blue, violet, right? And so, if I do that, I'm whatever, red, orange, I don't have yellow, green, blue. How many letters is this? Blue, violet, purpley, right? And then we get into, how many letters is that? 6. So I need 4 more to get all 10, right? 10 digits from 0 to 1. Violet, gray, and black. And then over here we do did you catch it? I don't know what it is. Well, you tell me. Look on the thing. That's actually good exercise. Oh, good. My mistake is it's exactly what I wanted you to do. Yeah. What goes after violet, gray, and white? Yeah, that dims out. I have my head over here, so white. And then I go, what goes before red? Look on the sheet. Brown. Okay, thank you. And what goes before brown? Black. Black. All right, thank you. Now life is good. I started to write that and go, wait a minute, I just wrote black. And so this is just a coding system. So what number goes with black? What? 0. Brown is 1, 2, 3, 4, 6, 7, 8, 9. There's a memory aid, but it's actually really kind of lewd. Old school, sexist. So it's got to be a better one. So look, I can write any number this way. And so what you have, if you take a look at your picture, if you look really closely at this tiny little thing, there's going to be lines on it, and hopefully you'll turn it, turn it whichever way. There's 3 that are kind of closer together, one that's a little bit farther away. And this one is either going to be gold or silver or none. And that tells you how much you can trust that resistor. These are cheaper to make. They didn't check them very carefully. So what does gold stand for? You tell me. 5%. What's silver? 10%. What's none? Like, that means that you can expect, you can depend on this to be within 5% or 10% or 20%. You're going to calculate the range of this value. And this value is going to be some color, some number. If it's red, what would it be? 2. And some color, which corresponds to some number. If it's green, what would it be? 5 times 10, or times that. You can do that. You can do times 10 to whatever power. If that's orange, what number would that be? 3. So it'd be 10 to the 3 or 1,000. Multiply times 1,000. And then you can take 5% of that, and that means it could be more by 5% or less. It's within 5% of that number. If you need help, call us over. You're going to check your resistance. You're going to be measuring resistance. We will have resistance. And are you okay? Any questions? So it's cool, the electronic circuitry. And again, you'd be surprised. You just build up. One class after another. All right, go for it.